right, y'all. So what we're going to be doing is we're going to be finding the inverse. This is the piece that we did. We started last chapter with it. Where, holy chunky pen. There we go. And we're going to take our y and we're going to take our x and we're going to make them change places. That's the whole point of finding the inverse. We change their place. So if we look at this first one here, I'm going to take my x and my y and make them change places. When I rewrite that, get my purple, there we go. It's going to give us x equals 3, that is a bad 3, holy cow. 3y plus 1. That is the inverse. It's just really, really bad math grammar. It's bad math grammar because we don't like x equals. We want to have it as a y equals. So that's our next step, is to solve this to be a y equals. What do I need to do to this guy to make it be a y equals? How do I get y by itself? On this. We will have to divide 3, but what should we do first? Subtract the 1. A little bit, 'cause got a bunch of friends being tardy. There we go. So we're going to subtract 1 from both sides. That's going to give me x minus 1 equals 3y. And now what are we going to do? Josh, you had this? Divide by 3. So we get that our y equals, and you can put it as one big like that, x minus 1 over 3. It's also exactly as valid to split it into 2 fractions. And if we were graphing, it would make more sense to split it into 2 fractions, where we had x over 3 minus 1/3, because then we'd have our slope-intercept form. So inverse functions is when we take the x and the y and we switch them. Let's look at number 2. Same general process. Hello, sir. Thank you. Oop, I'm going to give us a little wall here. So same general process. I'm going to take my x and my y and we're going to have them change places, just the letters. So we get x equals y squared. Just the letters change places. And now I want to get y by itself. I want to unsquare it. How do we unsquare it? Square root. So when we square root both sides, which I gotta get my green back, there we go. And this becomes the square root of x equals y. That's when we have those inverse relationships, these opposite signs, they undo each other. X squared is the inverse of square rooting. It's how we undo it. Last one, same process. We are going to switch my x and my y. That's how we make that inverse. It's going to give us x equals y cubed plus 2. What's our first step? Subtract the 2. When in doubt, start with your adding and subtracting. So we get x minus 2 equals y cubed. How do I get y by itself? We're going to cube root it. We're going to use that index, use that power. I want to get rid of that cube, so I have to do the cube root. Whatever I do to one side, we do to the other. So it's not pretty, but we just get the cube root of x minus 2 equals y. So inverse functions are going to come back around in our next chapter. So we need to remember what this inverse is. That's why it's there. Questions on any of these? Okay. We are going to go in your workbooks, page 399. And your book has a whole lot of table and pictures and things on there. But what they're really showing you here is an inverse operation. Just like, let's see, parabolas, looking at me, turn into square roots, and how the lines change direction. We're going to look at exponentials. And see, this one's our exponential, this one's an exponential growth, this is 2 to the x. When we do an inverse on them, they switch directions, and they look weird. And they look weirder as equations. What's up?
Is it the volume 2 book?
Yeah. Sweet, we've been in that for 2 chapters. I have to go get one from the office because I don't got it. In the math office. Yeah. Okay, so we've been living in exponential functions for a hot minute. 2 to the x, 3 to the x, 1/3 to the x. X was our exponent. In order to find the inverse, we have to pull our variable out of it, because when we create that inverse, just like we did in the bell work, where I switch where my x and my y were, we wind up with y in the exponent. And that's, at this point, not possible for us to remove. So we have to have a technique, a thing. And the thing was created because mathematicians, of course, they made a thing, and it's extra. To be able to pull the exponent out of the variable out of the exponent so that we could solve for y and graph it. So what we have is called a logarithm. And you can see how it's spelled at the top, because if I write it out, I will get it wrong. Ah, there it is. It is on the page. A logarithm. It is the inverse operation of your x and your exponent. That's what it is. It's how we undo it. And we are going to spend a lot of time practicing that, switching it back and forth. And I have a little bit of way for us to remember it, and I'm going to say it enough times that it's going to become annoying. And that it's, that is not the thing I want to circle. How that probably works better. And it's B, P, A, base, power, and the A stands for argument. I'm going to send this page down. So I'll write those words here so that you can see them. And this is how we're used to having it, where we have our base, same base we used in exponentials, and our power. We've used power before. That's a word we know. The A, we have that stand for the argument. It's what it equals. That's a T. Argument. To switch it around and get that power down, because that's the whole goal, is to get that whatever variable is in that exponent down, we switch it from BPA to log BAP, is the way that I remember it. And it's really, really just a matter of scooching the stuff down. Log base B, there's our base, of the argument, which I have as purple. Somebody's music's way too loud. I can hear it up here. Super rude. This is one of those super complicated and weird things that takes mental exercises to get over. So if you sit in here cranking your music while I'm talking, you're going to struggle on this one, and it's the first day in this chapter, y'all. BPA log BAP. Base power argument becomes base argument power. This is going to be something we use a lot. We're going to use this as we're solving. We're going to use this as we're rewriting. We're going to use this as we go through notation changes. We're going to use this almost every day. This is going to be something we need to know for this chapter. We're going to practice it a bunch. But BPA log BAP is one of those things we need this chapter. And the whole point is so I can take what was a power here, and look, my power becomes what this whole thing equals. So whatever my y was up here, if I switch this into a logarithmic notation, which is fancy schmancy talk for that thing with the log in it, what was my power becomes what the whole thing equals. And it's now a regular number, not a power. That's the whole point, is to pull the variable out. And I know, it's weird. Like, it's quite literally, you put the word log in it, which in fact is a button on the calculator, but we're not ready for it yet. So mostly what we're going to be doing is we're going to be switching back and forth today. So example 1 down at the bottom. I have our little form up here. Let me pay attention to what colors I had. Blue, pink, purple. Blue, pink, purple. Just because it's going to help me put our notations the same. I've got our little notation written up here. Oops, not argument. Because I'm going to rewrite it out. I know they've rewritten part of it for you guys there, but I'm going to rewrite the whole thing out. All we're going to do is we're going to look at this little code up here, and we're going to play match them up. What was my base, since they're giving it to us in logarithmic form? This little number at the bottom is the base. I'm going to try and circle it. There we go. So if I switch this to exponential form, my base is 4. Looking between here and here. My power, so the exponent on the 4 is whatever the log equals. 3. And that's going to equal the argument, which here is 64. So log base 4 of 64 is 3. All that means is 4 to the what is 64? 4 cubed is 64. It's all about switching around where they are. There are reasons we need this when it's got variables and stuff on it. We can't use the calculators to do this yet, because the calculators don't know how to do bases without a formula that we're going to do in 4 days? 3 days? I don't know. Change of base, I think, might be next week. But this is one of those things that you're going to take some mental gymnastics to do. So we're going to do the same dang thing. I've got my base of 3. I'm going to go over here and grab the power, which is over here, -5. Equals, oh, I didn't circle it over here. Whatever the middle of the log is, my argument, 1 over 243. And if you test that part, 3 to the negative 5, put that in your calculator, that we can do. You should get 1 over 243. We're not just making up values here. They are the same values. They just look weird. I'm going to do one more of these and then go the other direction. So we've got our base here, base 9. That becomes the base of my exponent. Same word, same meaning. Base of the log is the base of the exponent. Log base 9 of my power. So 9 to the 1/2 equals whatever this argument is in the log, whatever the log base 9 of m is. So 9 to the 1/2 is 3. Log base 9 of 3 is 1/2. They mean the same thing. These are equivalent. These are equivalent. These are equivalent. They mean the same thing. They just look weird, and we use them for different reasons. This side lets us solve for the exponent. This one doesn't. If we didn't know what this exponent was, 4 to the x equals 64, we'd be guessing and checking. Heaven forbid, what if it's a decimal? What if we had 4 to the 2.9? What if we had 4 to the 7/3? That'd be gross. The whole reason of logarithms is so that I could then solve over here and be able to play with the logarithms and figure out what that power is, especially if it's not a whole number. Whole numbers, we can often guess and check our way and get there. When it's not whole numbers, and especially not positive numbers, it's a lot harder. Questions on this go in the first direction. Okay. So I want you to try the check at the bottom. Try it. See, you can do it. Log base 125 of 5 is 1/3. Use the same thing. I've still got our little formula up here. B, P, A. The very bottom of the page. Give it a shot. All right. What's our base? What did we get? 125. What goes next?
1/3.
1/3 is our power. Equals what? 5. Good job, guys. Now we're going to do the same exact thing, other direction. We're going to take them from exponential form and put them in our logarithmic form. So this is page 400, next page. If you're curious, on that page 399, it has that historical minute. That's the dude who invented these. John Napier. He's the first person to have known written about them, but it's not very nice. Okay, and again, the book kind of gives you helping steps on this, which are not entirely helpful. But there's a lot of blank space next to it, so I recommend actually writing one up. But it's the same exact process. We are going to take our base power argument, BPA, and we're going to switch it around to be log BA equals P. So I'm going to take, and I'm going to write, not purple, log first. I will always kind of cursive my L. That's a me thing, not a requirement. It stops it from looking like 10G. So be careful when you're writing it. We don't want it to easily get confused with 10G. I always cursive it. But as long as you are aware of how you write your logs and pay attention to it. Which means, you know, when we're helping a friend, be careful. We're getting help from a friend. So we're going to have our log, and then we're going to look for our base. What is the base of our exponent here? 7. So log base 7. That's our base. Then comes our argument, whatever the exponent equals. So it's going to be this guy right there, 117,649. If you want to toss the comma in there, you can. Make sure it doesn't look like a period. I don't care. Commas are just decorative. And it's going to equal what the power was. It equals 6. When you're writing these, especially when you're putting them in to the textbook website, make sure you take this 7. When you type log in, it should automatically drop it down into the base. If it doesn't, you need to tell it there's usually like a little down arrow button on the top or in like the text box to make it go down like that. Because it's called a subscript to have it down like this when you're looking at coding. But that's down a level, kind of like how exponents are up a little half level and smaller. Log bases are down a half level and smaller. And that's how we write that in logarithmic form. I'm going to do the same thing over here. I'm going to get my log. And what's my base? 8. So BA is next. What's my argument? It's 1 over 512. It's whatever my exponent equals to. 1 over 512. And it's going to equal my power. -3. Yep. Log base 8 of 1 over 512 equals -3. Okay, let's do this next one. Same process. Log of what? What's my base again? 8. So this one again has a base 8. Log base 8 of what? 4. That's my argument. Equals what? 2/3. Yep, 2 over 3. That's my power. Okay, we're switching them back and forth. Do it by yourself now. Do the little check below it. 2 to the 9th equals 5/12. Put it in exponential form, or in logarithmic form. So switch it around. Base, power, argument, base. Still got our little formula up there at the top. BPA log BAP. So what do we get? Oop, that's not a pen. Hang tight. There we go. Log base 2 of 512 equals 9. So without the colors, this is what it looks like. Log base 2 of 512 equals 9. Make sure when you're writing them, whatever your base number is, goes down and is small. It should be lower. Like boop. Is cute. It needs to be down. Because otherwise it's going to look like log of 2,512, which is a different thing. Those two things are not the same. That 2 has to be lower and smaller. A good rule of thumb is if you've got like a line on your page, you can do your log like you would normally write on a line and just put your 2 underneath it like this. Log base 2 of 512 equals 9. So if you're writing on lined paper or using that line there, put your base just below the line. Okay, that helps us remember to put it down. Questions on these, on switching between the forms? Because what we're going to do is we're going to evaluate our first one, which they picked a lovely, super duper helpful and easy one for us. They made a good choice. Not really. Especially because they didn't put an actual power on here for us, so we're going to fix that. The book uses Y because they like to be jerks, but that's okay. So this is example 3. When they tell you to evaluate an expression like this, what they mean is put it into exponential form. But they didn't actually tell us what this equals because that's what we're trying to find. So we're going to add in an equals Y. So log base 216 of 6 is what? We want to know what that equals. And since we don't know it, we put a variable. Since the book used Y, I'm using Y. In order to evaluate it, to solve it, we're going to switch it into exponential form because that's something we actually know how to work with. So I'm going to take my base power argument, BPA log BAP, and we're going to switch it around again. But now we're going to have a variable in it. So my base is 216. Excuse me. 216. My power is Y. And it's going to equal 6. We look at that and go, great. That's super helpful. The book gives you a clue because they give you a whole lot of work on here. 216 actually does get to that common base. Just like when we solved in exponentials and we get it so that they had the same base. 216 is the same thing as 6 cubed. So we can really write this as 6 cubed. Stylus is freaking out. To the power of Y equals 6. What exponent is on this 6 as it sits right now? This one. What exponent does it have up here? It's 1. So now we're firmly back into the chapter 7 stuff. They have those same bases. Can we solve this? We just did on that chapter test we took last week. What happens when I have a power and a power here? What do we do with the 3 and the Y? 6 to the third to the Y. What happens when I take the power of a power? What do I do with the 3 and the Y? multiply them. 6 to the 3y is this equals 6 to the 1. What can I do now? Drop the 6's. We don't need them anymore. Once the bases are the same, all we have left is 3y equals 1. So what does y equal? What do we do to get y by itself? We're so close, y'all. Divide by 3 on both sides. Y is 1/3. So this logarithm up at the top, log base 216 of 6. Log base 216 of 6 equals 1/3. We can calculate a logarithm. This is how we can figure out what an exponent is. We're going to get to the point where we can do these a lot faster as we go through it, but it's going to take us some time. And these are going to be a struggle for a little while, and that's okay. We have time for that. So, oh, I didn't put the homework up here. I love that for me. There it is. I did put it up here. Homework 8-1. These are the numbers. We can do this set today. 1, 3, 5, 7, 9, 13, 18, 20. I am about 50% sure I have it up on the Canvas page, but I'm pretty sure I don't have the Canvas page actually imported. So I will get it up tomorrow or the next period or third period because I did not get a chance to import it before I went on break. So we will have time. Tomorrow we are going to be looking at graphs of these, and y'all know how I feel about the way the book does graphs, so we're going to be gluing graphs into your books a fair amount because the book's a jerk. So y'all have 6 minutes until announcements start. You can do the homework on paper, like it's the same questions, same exact questions as are on page 405. So you can start it there, and that way you either just have to type it in, or you can do it on paper and turn it in on paper. I'm okay with that too, especially since I don't have it in there yet. All right, so yeah, that's what I got for you today.